Hazel, you're okay.
Good morning, Spicy Pepper. Good morning.
Hazel.
Yo, yo, yo. Ahoy. Wait for a couple more viewers. Hola. Salutations. Hmm. Yo voy empezar mi lección. Okay. So, today, we are done with momentum. And now we are going to move on to our next topic, which is circular motion. Okay. And so we're going to start off with some derivations. Okay. Okay. So first of all, I want to talk about a little bit about vectors. Okay. If we have a vector that has a length big R and it makes an angle theta with the horizontal or with the x-axis, then the vertical leg of the triangle would be r sine of theta. Okay, and the horizontal leg of the triangle would be r cosine of theta. And so we could write this position vector as r cosine of theta times I hat plus r sine of theta times j hat. All right? Now, what does it mean to be moving in a circle? Okay. If you're moving in a circle like this, then that means that as time goes on, the angle is changing. Okay. And so we're going to say that the angle is equal to omega times time. All right. So as time goes on, the angle gets bigger, and so this angle is going to change, and it's describing an object moving around in a circle. Okay. So if something is moving in a circle, its r of t is going to be r cosine of omega t times I hat plus r sine of omega t times j hat. Okay? So that this is the vector representing something moving in a circle. Okay? It makes an angle theta, but the theta is changing as time goes on. So the argument of the sine and the cosine are changing. Now we can think about if you go around once, okay, by the way, omega is called the angular velocity, okay, and we can see from this relationship that omega is the derivative of the angle with respect to time, okay, so you should know that. There's going to be a lot of definitions in this lesson. Okay, so this tells us that the angular velocity has units of radians per second. Okay. Another thing we can notice from this is if you go around the circle completely one full time, then that means theta equals 2 pi. All right. And the time elapsed to go around the circle is denoted by capital T, and that's called the period. So we can see from this relationship that if one period elapses, then you've gone all the way around the circle so that your angle is going to be 2 pi. So we can see that the period is equal to 2 pi over omega. So this is called the period, which is equal to the time to go around once. To go around the circle once. So what we're going to do is, now by the way, if I look at before I go into my derivations, I just want to do a little thing. What if I do the magnitude of r of t? What would that be? Well, I would do the x component squared, so r squared cosine squared of omega t, plus the y component squared, r squared sine squared of omega t, and then I would take the square root of that. Now see how we have cosine squared plus sine squared, so that's just equal to 1, so we get square root of r squared, which is just r. So the distance from the origin is always going to be the radius of the circle. See how that works? Because of cosine squared plus sine squared equals 1. All right. So now what I would like to do, okay, is I would like to derive a lot of the equations for circular motion that we used last year, okay? So, for example, let's get the velocity as a function of time, okay? The velocity as a function of time is the derivative of the position vector as a function of time. So how do I take the derivative of a vector? I take the derivative of the I component, and I take the derivative of the j component. This is taking the derivative of a trig function. So kind of one of the bummers about this class is it's always a little bit ahead of the AB calculus course. So you might not know how to do that yet, but this is just for the derivation. You can come back and watch this lesson again after you learn about derivatives of trig functions. So taking the derivative of cosine gives negative sine. And then the chain rule, so we do the derivative of the outside function times the derivative of the inside function. The derivative of omega t with respect to time is omega. Okay? So, so that's the I component of the velocity. And then we take the derivative of the j component. The derivative of sine is cosine. And then the chain rule, when we take the derivative of the inside function, brings out a factor of omega. So we have, this is true. Okay? So this is the velocity vector as a function of time. Okay? So now what we can go ahead and do is we can find the magnitude of the velocity vector. So we do the Pythagorean theorem on that. And actually the way that it works, okay, is that we would do x component squared times plus y component squared square root. Again, we're going to have a sine squared plus a cosine squared. And so you end up getting r times omega. Okay, so this is the speed in circular motion, is r times omega. Notice that angular velocity is not the same thing as speed, because speed is measured in meters per second. Angular velocity is measured in radians per second. So r times omega. Now, if we take omega and we write it in terms of the period, we could also say omega is 2 pi over the period. So I could write this as 2 pi r over the period. So this is an equation for the speed in circular motion. Okay, so I like this equation a lot because it says speed is distance over time, and if we think about the distance around a circle is its circumference, which is 2 pi r, and the time it takes is the period. So it takes, the distance traveled is 2 pi r, the period is capital T, we divide them, we get the speed. So these are two alternative equations for the speed. All right. Another thing I wanted to point out is that we could take the dot product of the velocity with the position. So what if we did the dot product of velocity with position? Well, it would be x component times x component. So the x component of the velocity is minus r omega sine of omega t. The x component of the position is r cosine of omega t. Okay, plus y component times y component. Y component is r omega cosine of omega t. Okay, and then y component of the position is r sine of omega t. So you can see that we have negative sine times cosine, and then we have positive sine times cosine. So this is actually equal to 0. Now, does anyone know? Type it into the chat if you know. What does it mean if two vectors have a dot product of 0? Type it into the chat if you know. And I will just continue to suffer because Hazel is laying right next to me on the ground and she is farting up a storm. Absolutely farting up a storm. Perpendicular, excellent. So having a dot product of 0 means two vectors are perpendicular to each other. So what that means is that the velocity is perpendicular to the position vector. So you're moving in a circle. Here's the position vector. The velocity is perpendicular to it. So wherever you are in that circle, if you're over here, then the velocity is going to be perpendicular to that radius vector. Okay, this is one of the facts that we learned last year. I told you that the velocity is tangent to the circle, and I gave you an equation for the speed, which was 2 pi r over the period. So kind of the purpose of this first part of circular motion, of my circular motion lesson, is to derive a lot of the results that we just kind of stated in AP Physics 1 or in IB Physics. So the velocity is perpendicular to the position vector in circular motion. Awesome. Let's go one step further and let's get the acceleration as a function of time. So velocity as a function of time was minus r omega sine of omega t I hat plus r omega cosine of omega t j hat. So we're going to go one step further and find the acceleration as a function of time. Okay. So taking the derivative of sine gives cosine. Well, I'll just write it as dv dt. Taking the derivative of sine gives cosine, and the chain rule brings out another factor of omega. Okay. So we get negative r omega squared cosine of omega t times I hat. Okay. Plus, we got to take the derivative of this. The derivative of cosine is negative sine, so this should be a minus sign. And then the chain rule brings out another factor of omega, so we get minus r omega squared sine of omega t times j hat. Okay? So a couple of things. The first thing is that the magnitude of the acceleration is r omega squared. Okay? The magnitude of the acceleration is r omega squared, because you get cosine squared plus sine squared. So that becomes 1, and so the only thing that remains is r omega squared. All right? Omega, we know omega can be written as 2 pi r over, or 2 pi over the period. So I could also write this as 4 pi squared r over period squared if I wanted to. Okay. Or I could notice that r omega is the velocity, and you can actually write this as v squared over r, speed squared divided by radius. So this acceleration, why is the object accelerating? Well, it's accelerating not because its speed is changing. It's accelerating because the direction of the velocity vector is changing. Okay? And so that is called centripetal acceleration. Okay? And I've just given you 3 equivalent formulas for centripetal acceleration. All right? These 2 I used last year in AP Physics 1 or in IB Physics, and this one is an equivalent form that's just expressing it in terms of angular velocity. Okay? The other thing I wanted to point out is that the acceleration vector is actually equal to negative omega squared times the position vector. Okay? You can see that it's cosine sine, just like the original position vector was cosine and sine. And we have the r, but we have this negative sign here, and we also have omega squared. So what does that mean? Can you remind me, what does it mean if we take a vector and we multiply it by negative 1? What does that do? Right, so it's in the opposite direction. So we can see that so this means that A is in the opposite direction to R. Okay? Now let's think about that. The R vector points from the center of the circle to the edge. So that means that the acceleration points from the edge of the circle back towards the center. Okay? So one of the things I taught you last year was that the centripetal acceleration always points towards the center of the circle, no matter where you are. Okay? So this is proof of that. A is in the opposite direction to R, so it points towards the center of the circle. So the centripetal acceleration points to the center of the circle. Cool. So what I've just done is I have proved all of the facts that we learned last year about circular motion. So I think that's kind of neat. I hope you enjoyed that. So, Newton's second law applies to circular motion. Okay? Newton's second law applies to circular motion. Okay? So we are going to use this to analyze something called a conical pendulum. So what is a conical pendulum? A conical pendulum, we have a ceiling, and we have a string. The string has a length L. On the end of the string is a bob of mass M, and the mass is moving in a circle, so it's basically sweeping out a cone. Okay, sweeping out a cone, and depending on the speed of the mass, it will make different angles with the vertical. Okay, it'll make different angles with the vertical. So this is kind of a three-dimensional view. So this is a 3D view. But what if we were to look at this from edge on? What is this going to look like? Well, you'd have your ceiling. Here's the mass. And it's basically going back and forth. So, you know, if you look at a circle from the edge on, it just looks like a line. Okay? So that it just looks flat. All right. So this is theta. This is the length. Because the mass is moving in this circle, it's a horizontal circle. You see, it's moving back and forth horizontally. So this means that the y component of the acceleration is 0. Because if the y component of the acceleration was not 0, then the mass would be rising or falling, but it's just moving in a flat circle. Okay. The x component of the acceleration, I should probably say the z component of the acceleration is 0, because we have, this is sort of three-dimensional, right? We have the z direction going up and down, and we have the xy plane horizontally. Okay. The x component of the acceleration points to the center of the circle. Okay, so it points towards the center of the circle. That's the direction of the acceleration. The acceleration points towards the center of the circle. The velocity, of course, points tangent to the circle. So in this case, the velocity would be out of the page towards you. Okay, so let's analyze this. First of all, I'm going to draw a free body diagram, and we're going to consider the mass when it is at this instant. When it's at this instant. So there is a force of tension. I'm going to call it F sub t for this problem, okay? Because we also have period, which is represented by capital T. All right? And that angle is theta. Then we also have the weight force, mg, which points vertically downward. And that's it. Okay? So what I could do is I could take this diagonal force and I could break it up into a vertical force and a horizontal force. So I can see that tension, the diagonal tension is actually equivalent to an upward tension of size f sub t adjacent to the angle, cosine of theta. And then a leftward tension, which is f sub t opposite the angle, so sine of theta. And then we have a downward weight force. Okay? So let's do Newton's second law in the vertical direction. So the net force in the z direction is equal to m times the acceleration in the z direction. But as we said, the acceleration in the z direction is 0 because this mass is only moving in the horizontal plane. It's not moving up or down. Okay, so that's 0. Now what is the net force in the z direction? We have an up force of f sub t cosine of theta. And we have a down force of mg. So what that says is that the tension is equal to mg over cosine of theta. All right? In particular, what if this angle were 90 degrees? 90 degrees would mean that the string is actually horizontal. And if theta is 90, well, cosine of 90 degrees is 0, so you would have infinite tension. So if you think about whirling something on the end of a string in a circle, you can never make it perfectly horizontal. In order to make it perfectly horizontal, you would have to have infinite tension, which would break the string. Okay? Now let's do the net force in the x direction. In the x direction, we have a leftward force that is of size f sub t sine of theta. And that equals m times the x component of the acceleration. We can see that at this particular instant, the acceleration is going to be to the left. And because it's moving in a circle, the acceleration is given, that's right here, by a centripetal acceleration, 4 pi squared r over period squared. Okay? So it's going to be negative, so equals negative m times 4 pi squared r over period squared. Now we have to be a little bit careful here. The radius is not the same thing as L. Because if we look at this circle, the radius is this distance right here. So it's a leg of the triangle for which L is the hypotenuse. So we can actually see that this distance right here is L sine of theta. So the radius is L sine theta. So I have minus f sub t sine of theta equals minus m times 4 pi squared L sine theta over period squared. So I can see that the sine of theta cancels out, the minus signs cancel out as well, and I get f sub t equals m times 4 pi squared L over period squared. F sub t is, of course, mg cosine of theta. Mg over cosine of theta, excuse me. So we can actually use this to solve for the period of the conical pendulum. And if you do that, you get period squared equals, well, masses cancel out. It equals 4 pi squared L over G times cosine of theta. So this is an equation for the period of a conical pendulum. All right? So your quiz for today is going to deal with just these fundamental circular motion concepts and analyzing the conical pendulum. And then for the next lesson, we will build up complexity and do some more challenging circular motion problems. Okay, so that's my lesson for today, and I'll see you.